So now let's look at a little bit more of the scientific units used to measure things like emission and absorption in terms that we care about in this lab. And the first thing I want to touch on is brightness as perceived from lighting and display. So we talked about white LEDs, but how do you measure how bright it is? Well, what you typically do is you measure things in terms of their luminous intensity. Okay? And so this is a plot of the human eye response. Photopic is the light state, and this is the dark adapted eye. So we focused on the light state here, which is daylight, in a daylight setting or an office setting. And what you'll see is the human eye becomes more and more sensitive to light as you go to the green, and then it drops off again as you go to the red. Okay? And so that's why we can see, of course, the visible spectrum. The peak is at 555 nanometers, where 1 watt of light will give you 683 lumens of brightness. Okay? That also happens to be where the photopic and the scotopic curves actually overlap here too, which is interesting. Okay? So, if I look at green light, again, right here at the middle, that's where the eye sees the most brightness. And so the lumens are, it's not an actual scientific unit, rather it's a unit representing, it is a scientific unit, but it's more of a unit representing the brightness that the human eye would perceive from light. If I go out to the blue, it's much lower efficiency. You can see it drops down here when you go over to here to about 50 lumens per watt compared to the peak at 683. And then the red is also less than green. When you get out into the red, it drops down to around 250. And so the green is the most efficient as brightness seen by the human eye. Red is second, and blue is the least efficient. If you go beyond that, then everything starts to look basically black. You don't see much of anything at all, which makes sense when you go out to the ultraviolet or the infrared. So when you look at this, you're like, well, why is the human eye adapted so well to green light? Well, there's two reasons. One, if you look at the peak of sunlight, the intensity of sunlight, in the visible, it's right around green. And also think about the world around us. There's a lot of green with chlorophyll and things like that. So a lot of the reflection, green and yellow and things like that around us, peaks out in this spectrum as well. If someone ever tries to sell you a white light source that has a theoretical maximum, they say, of 683 lumens per watt, tell them that that's not possible, because a white light source, again, has to mix the blue, the green, and the red. And so when you look at the theoretical maximum, when you combine all the lights to create white light, it's only in the range of 200 to 300 lumens per watt. So that's about the best as you can do. Within that context, then, you can look at the efficiency in lumens per watt of different types of white lights that are available. Here's incandescent light bulbs down in the 10 to 20 lumens per watt. Fluorescents get you to around 100 lumens per watt. This is versus year too. And then you can see white LEDs where they're rapidly marching toward the maximum efficiency, which is a little bit above 200 lumens per watt for a white LED. Now, if you look at LEDs and their optics in terms of getting the light out, the LEDs themselves are isotropic emitters. That means that the photons inside are generated in all directions equally. However, refraction and total internal reflection can change the radiation pattern as it exits a packaged LED. So if this is an LED right here, and this is some epoxy over it, if you would expect the light to be equal in all directions, it's not. In fact, when you see it trying to exit the surface, as you get to angles that are closer to the critical angle, then the intensity decreases, right? And so the maximum intensity is straight out. I go at this angle, it decreases, and at this point I'm almost close to the critical angle. And of course at these angles you won't see anything because at that point it's totally internally reflected. And so this flat LED actually has a Lambertian profile where the intensity falls off with the cosine of theta. Okay? Here's a hemispherical LED, which is set up such that if the emission is here, the light is incident on the glass air surface here at the same angle regardless of the emission area, so the intensity is equal for all directions. And then you could do a parabolic shape like you have here, which can actually act like a lens and focus it into more of a, not quite a cone, but more of a parabolic intensity pattern, which is more forward focus than you would have with either of these approaches here. So if we're talking about light and total internal reflection, how much light escapes from, let's say for example, a gallium phosphide LED, which would be greenish yellow in color. Well, if this is the LED and it has a high refractive index inside, which for gallium phosphide is 3.4, and this is air, then we know that we always will have some Fresnel reflection, even if we're outside the critical angle where we can get refraction out, we still have some Fresnel reflection. So there's some loss there. The bigger issue is if you get to the critical angle, then the light is totally internally reflected. So it can be very difficult to get the light out if you get to the critical angle. And so if you look at this, if this is where the emission photon was emitted, these cones are the only escape paths where light is outside the critical angle and can refract out. And if it emits, for instance, in this direction here, it'll be total internal reflect because that's outside this cone. And so you can calculate that approximately the amount of percentage of light that can get outside each of these cones is 1/4 times the refractive index of the LED squared. So here's an example for gallium phosphide. Fresnel reflection will cause you to lose about 30% of the light, so you'll get about 70% out. And if you calculate the critical angle, you find out, and you do this calculation, you find that you only get 2% escapes at each of the 6 sides. Only 2% at each of these. And so that's 12% total, okay? Times the 70% because you have loss with Fresnel reflection. So for the first pass, you only get 8.4% out at best. And so if you look at modern LEDs, they'll do things like this to help get the light out. For example, here, they've changed the shape. So as the light is basically reflected back in, that'll keep redistributing the angles. So at some point, it'll hit an angle where it can get out. Because if it was a perfectly square type LED, it could be at an angle where it would just basically keep circulating around and be tracked. The slope sidewall redistributes the angle, so at some point it can find its way out beyond the critical angle. And here's a simple derivation of how to get that 1/4n squared. So they talk about this and go through the mathematics of how you come up with this. And to improve the light out coupling, you can also, instead of, one way to do that is say, well, okay, if I don't want total internal reflection here, let's just make this surface rough or design it such that it improves the outcoupling. So one way you could do that is shown here, and another way is this way. One of these is refractive, the other one is diffractive. Which one's which? Well, this is probably the refractive one, you could tell, because the features are pretty large. This is using like a photonic crystal on the surface and using optical interference to help force the light out of the surface. And these uses lenses here where basically if light's coming at an angle like this that would be totally internal reflected, it could hit the lens here and get out. If it's coming like this, it can get out. And if you look at how these lenses do, they actually increase the amount of light that can escape compared to a smooth surface. Also, looking at more units and things like that for emission, we should be looking at some more of the finer details for optical absorption as well. So what's absorption look like? Well, we know practically that not all the photons are absorbed instantly at the surface, so they must penetrate a bit of distance before being absorbed. Unless, of course, it's something like a metal. And so what's this look like for a material that's opaque but not as opaque as a metal, for example? Well, let's look at, we can simply derive this pretty quickly. Here's my photon intensity coming in. Here, for example, is a material that can absorb light, like silicon, and then here's how much light I have at the other side. And so I say, well, my difference between my starting intensity and the intensity I have at a distance dz in here is equal to the intensity times the amount absorbed over the distance dz. So alpha and dz, and alpha is the amount that's absorbed over that. So I just reorder this. I get the following differential equation, which is pretty easy to solve if you look at it, because the derivative of the intensity is equal to the intensity times a constant. And so this constant fell out, and this didn't change. And so I'll skip past this, but it's exponential then. And so the solution for this is a exponential, where the intensity at a position z here, at any position z into this, falls off exponentially with distance z from the original intensity according to this absorption coefficient here, which has units of 1/centimeters, which makes sense because I can't have units up in the exponent, right? So centimeters cancels out with 1/centimeters. And you can see that exponential fall off here as you're going here. So if I have a small absorption coefficient, which means it's a weak absorber, most of the light could get through. If I have a large absorption coefficient, it could all be absorbed over a very short distance and almost none of it get through. Here's a simple calculation. I'm going to do this for a semiconductor example, but we'll be doing it also this week in lab with plastics with dyes in them. For semiconductors, the absorption only occurs at the band gap, so you have to have enough photon energy to excite electron-hole pairs. And so let's look at an example for silicon. The wavelength is decreasing. Eventually you get to wavelengths which are short enough to have enough energy to excite electron-hole pairs, and then the absorption coefficient starts to increase here. Okay? And so look at the example here for, let's say, for silicon. How thick does the silicon need to be to absorb 90% of 1 micron light that hits it? So if I'm at 1 micron, I'll assume that roughly, if this is log of absorption, then that's 100, because log of 2 gives me 100. And so I'll assume my absorption coefficient is 100. I'll calculate that, again, I want to get to 90% absorbed, so 10% left is equal to e to the minus, I put in 100 for alpha, z. I'll solve for z, and I'll find that it has to be 230 microns thick to absorb 90% of the light. Do the same calculation, but do for the peak of sunlight, green, where the absorption coefficient is increasing substantially as we go towards green light, which is right here. Then you find it only has to be 2 microns because the absorption coefficient is that much higher. Just 2 microns to absorb that same 90%. So do some more review, take a break, and we'll keep marching on from there.